Okay, I'm going to start working out the text quiz answers. Okay, the first problem, it says just tell whether it represents exponential growth or decay and explain. So what we're going to look at is the base. If the base is fractional between 0 and 1, it's decay. If the base is greater than 1, it's going to be growth. So let's take a look here. We have 4.25. So 1 will be growth. That's definitely greater than 1. For number 2, I have a base of 3/8. Well, 3/8 is less than 1. I mean, it's between 0 and 1. So that's going to be decay. For this one, E is the base. And so the base here is, again, greater than 1. We're not going to look at the exponent. That's not what determines that. So that's growth. And in the last one, we have 5e to the minus 2x. Okay, so let's think about that. E to the minus 2x, that's going to be 1 all over e to the 2x. And we know that e is about 2.7. So this is really going to be 1 over about 2.7 to the 2x. So this part right here is the base. And I should have moved the exponent up a little bit. Now let's just try that again. Or I could have written that as 1 over 2.7 to the 2x. That's probably a better way to show it. And the base is fractional, so this is going to be decay. Okay, the next thing says simplify. So we, excuse me, we are going to start with number 5. And in this case, we have the bases are the same, so the exponents add. We're going to have e to the 8 plus 4 is e to the 12. For number 6, we have a numerator and a denominator, so the exponents on the e's will subtract. We have 15 divided by 3. That's going to be 5. And then e cubed minus e to the first will be e squared. Number 7 is going to be the cube will multiply by the exponents. It's on the 5, which is a 1. So that's going to be 5 cubed. And then the 3 will multiply by the exponents. It's on the e. So 3 times 4x is 12x. And let's go ahead and make that 5 cubed is 125. Okay, so for number 8, when the bases match, and this is an ln, so it's a base e, if I have an exponential, and the power on it is a logarithm, if the bases on the logarithms match, it's just going to be the number that I'm taking the logarithm of in the exponent, so this will simply be equal to 9. Over here, the bases don't match on the 7 and the 49, so if I have a logarithm and what I'm taking the logarithm of is an exponential, then I need to get the bases to match, and then it's just going to be whatever the exponent is. So for number 9, let's go ahead and say that's log 7 of 7 squared to the x. So log 7, and these two exponents will multiply. So log base 7 of 7 to the 2x. Now my base on the log and the base on the exponent match, so that's simply going to be whatever the exponent is, which is 2x. 10. Same kind of a situation. We need to get the 81 somehow to change that into a base of 3. So that'd be log base 3 of 81 to the minus 2x. And let's change that 81 into a base 3. So that would be 3 to the 4th power. And that'd be the minus 2x. Now then, the exponents will multiply. So I have log base 3 of 3. Now 4 times a negative 2, that would be to a negative 8x. Now my bases match, so it's going to be whatever the exponent is. So that's going to be to a negative 8x will be my answer. Okay, the next one just says rewrite the expression in exponential log form. So I'm going to change their form. So the first one, it's going to be 4 to the 5th is equal to 1024. The next one will be 1/3 to the minus 3 is 27. Number 13, the base of the logarithm will be 7. What's outside the log, what's outside the exponential all alone will move inside. And then what's trapped in the exponent position will move outside all alone. And number 14, same kind of a problem. I'm going to have the base, so it's log base 4, will move to the base. What's outside of the log, outside of the exponential will move inside the log, so the piece that's all alone will move inside. So I've got 0.0625. And what's up in the exponent position, trapped up there, will move outside. And let's do the next one. I'm going to need a calculator for this, it looks like. So the first one is log base 10. Now, we don't show the base 10, but I'm just putting it there so you know that you can use a key on your calculator, your logarithm key. So we'll just simply type in log of 45. So how that would work is these are the keystrokes on the calculator. Log, and then I get a parentheses, and I would put 45 in there and be sure to close those parentheses. And I've got 1.653. Number 16, now I'm going to use my natural base logarithm key. And so I have ln of 1.4. We would close the parentheses in the calculator. And I've got 0.336. And number 17, we're going to need to use the change of base formula. So what that's going to be is, let's change it into a base 10 log. So that would be the log. Actually, that's one I can just do in my head, right? So what we're going to say is 2 to what power is equal to 32. And that answer is going to be 5. Okay, the next problem says graph the function and its inverse, and I'll probably state the domain and range and the asymptote also. So the first thing we want to do is come up with the parent function. Well, if we look at number 18, that is a parent function, so let's go ahead and get some points to plot. So on my parent table, I'm going to have x and I'm going to have y. And let's pick some values. I'm going to pick a -1 for y. For x. I'll pick a 0 for x, and I'm going to pick a 1 for x. And for an exponential, I am going to pick the x and get the y, just like always. So what I'm going to have here is I have 1/9 to the -1. Well, that's going to flip the 9 up to a numerator, so I'm going to have 9. And then for 0, I'm going to have 1/9 to the 0. That's going to be 1. And when I have 1/9 to the first power, that's simply going to be 1/9. Okay, so the asymptote of this is going to be at It's an exponential, so the asymptote's going to be at y equal to 0. Okay, we can see that at a negative, when x is a negative 1, I'm going to have 9 for y. We would expect this to be a decay. 0, 1, that will be on all parent graphs, remember. And then 1, 1/9. So this is going to come down and go along the asymptote, not ever equaling 0, but getting closer and closer. The domain is going to be x is equal to all reals. Oops. And the range is going to be y greater than 0. And now let's do the inverse. And let's go ahead and make the inverse equation. But when I plot it, I'm actually going to plot, I'm just going to switch the points. So I've kind of got my domain and range in the way. So I'm going to have f to minus 1, f, the inverse of x. What I'm going to have for my xy table are a change of values. This is the inverse. And I don't know what that equation is yet. We'll figure that out. So what's going to happen is the x and y values switch. 9, negative 1, 1, 0, 1/9, 1. And let's plot that. So I have 9, negative 1. I have 1, 0. And I have 1/9, 1. And let's find the equation and the domain on that. For the inverse, the domain is going to be all real numbers where x is greater than 0. And the range is going to be all real numbers. So we can see it's going up forever and down forever. And my asymptote on that was at x equal to 0. It's a line, so you have to state it as a line. Now let's go ahead and find the equation, the inverse for that. So if I had, the original equation was y is equal to 1/9 x. Switch the x and y. Okay, we need to get the y alone, so let's change it into a logarithm. So that's going to be log of 1/9. What's outside the log, or the exponential, the x will move inside, and the y comes out alone. So that would be the equation of my inverse. And we're done with that problem. Okay, let's start the next problem. So what I have is I have the ln of x minus 7. And what we're going to do is I'm going to do this by hand. So instead of plugging numbers in, I'm going to plot a parent, and then I'm going to shift it. So what I'm going to do first is make a table of y equals ln of x and find my x and y values for that. I'll use 3. And so the first thing I'm going to do is if I pick x equal to a negative 1, actually we're going to pick a y, sorry, and find x because it's a logarithm. Let me figure out what that is real quick. Okay, let me show you again how we do that, right? So I pick the y, and what that's going to be is, if we look up here, that's e to the y, so it's e to the y is equal to x. And so if I put the negative 1 for y, I get 1 all over 2.718, which is equal to 0.37. So 0.37. Okay, let's go ahead then and do 0. So e to the 0 is equal to 1. And then when I do e to the 1, right, because we're going to take e, remember, e to the y is equal to x, and we're picking y equal to 1, so that's going to be 2.7. Okay, now if I take a look, I've got, in my equation, I've got h is equal to 7. So the x values are going to switch by 7. So for the y equals ln of x minus 7, I'm going to have x plus 7. And my y values will stay the same. So I've got 7.37 minus 1. I have 8, 0, and I have 9.71. Okay, and I'm going to plot that in just a second. Let's go ahead and do the inverse. So down here is where I'm going to put the inverse. So I have y is equal to the ln of x minus 7. Let's switch the x and the y. X is equal to the ln of y minus 7. So I'm going to change this to an exponential. So I've got e to the x is equal to the y minus 7, right? So we go e to the x is equal to y minus 7. And then I'm going to add the 7 over, so I've got e to the x plus 7 is equal to y. There's my inverse. So the inverse is equal to e to the x. And for the x and y values for that, I'm simply going to switch the x and y coordinates. So I've got a negative 1, 7.37, 0, 8, 1, 9.7. So let's plot those. I'm going to change this to blue. Okay, let's plot the parent. The logarithm graph that they gave us. So I have 7.37 negative 1. I have 8, 0. And then I have 9.71. This would be my asymptote here out at 7. Because my asymptote will be at h. So this graph is going to come along, swing out. The domain, and I'm not going to put it because I don't have a lot of room, is just going to be x greater than 7. The range is going to be all reals. You could put that interval notation. Now let's go ahead and plot the inverse. And the inverse is going to be a negative 1 for x, 7.37. Zero 8. and then 1 9.7. So I don't really have very good detail here on this graph. But the asymptote is going to be moved from a asymptote at x equal to 7 to a y equal to 7. So 1, 2, 3, 4, 5, 6, 7. So here's going to be my asymptote. Remember, when I take the inverse, what is x becomes y and y becomes x. So the asymptote at x equal to 7 becomes an asymptote at y equal to 7. And then this graph will come along like this and swing up. And the domain of that graph will be all reals. X equals to all reals. And the range of the graph will be y greater than 7. Let's move to the next one. Okay, on the next one we have y is equal to log base 5 of x plus 1. So I've already put the equation, which is be my parent. The shift is going to go away for my parent. And if you look at this, you can see that x minus h, so h is equal to a negative 1. So my shifted graph is going to be x, since h is a minus 1, I'm going to shift my x by 1, and my y will stay the same again. Let's go ahead and find the inverse right now, and we'll put it over there, but we won't plot it immediately. So what we have is we have y is equal to log base 5 of x plus 1. So we're going to switch the x and the y. X is equal to the log base 5 of y plus 1. So then we're going to have 5 to the x is equal to x plus 1. And then, y plus 1. And now we're going to subtract 1, so I got 5 to the x minus 1 is equal to y. And there's my inverse equation. So that will be all right, and x and y values for that. Okay, so let's go back and fill in some values. So what we have is, remember, for a logarithm, we pick the y, we get the x. So minus 1, 0, 1. Let's do those. So 5 to the negative 1 would be equal to x. That would be 1/5. 5 to the 0 is equal to 1, and 5 to the 1 is equal to 5. Now I'm going to shift the x values by 1 because that's what the original equation was. So 1/5 minus 1 would be a negative 4/5. 1 minus 1 is 0, and 5 minus 1 is 4. My y values don't change. And then for my inverse, the x's and y values will switch, so that'd be a negative 1, negative 4/5. I would have 0, 0, and I would have 1, 4. Okay, so let's go ahead and plot some of these. Now, let me do the domain and ranges while we have a chance. So the domain of the original graph, this one right here, we're going to have the domain. It's going to be all reals where x is greater than a negative 1, right? Because h is a negative 1. The range is going to be all y is equal to all reals. And then my inverse graph, which is this one, we're going to have the domain x equals to all reals, and the range will move to y greater than a negative 1. So let's go ahead and plot these. So we already said the x would have an asymptote at x equal to negative 1. And one of my points is going to be a negative 4/5, negative 1. Another point is 0, 0. And another point is 4, 1. Now let's do the inverse. Okay, the inverse we said was going to have an asymptote at y equal to a -1. And we have a point, a -1, a -4/5, then we have 0, 0, and we have 1, 4. So it'll come along the asymptote and swing up like exponentials do. And there's that graph. So let's look at 21. Okay, for the next one, they give us an equation of a parent, and they want us to find the equation of the shifted graph. Okay, so let's take a look at this. For a parent graph, we would expect the asymptote here to be at, for the parent, the asymptote is going to be at x equal to 0. So we can figure out what the h value is by seeing where the asymptote went. So over here, we can see that what we really have is we have the asymptote at x equal to 2. So what we have is we have h equal to 2. So already I know that this thing must have something where it's got the log base 3 of x minus 2. Now what we need to do is the one point that is the same for all logarithms, parent graphs, would be the point 1, 0. So what happened to the point 1, 0? It normally would be here, because this has got some weird scales. That would be 1, 0. We would have expected that point, if all it has was an x shift, to move from 1, 0, then over 2 to be at 3, 0. We'd expect it to be right there. But it's not. If we look, it's actually then also moved up to here. So it's gone up 1 also. So it's moved to the right 2 because of the shift that we have in the x, which is h, and then it's moved up 1. So I can see that actually my equation, and they don't use f for this shift, they use the g, that my equation would be this. Okay, moving on to the next one, we see that we have an exponential, and here's the parent. And remember, the parent graph of an exponential will have the asymptote at y equal to 0. That's the asymptote. So if we see where the asymptote goes, we can see what the shift in the y direction is. And we know that it also always, the parent graphs will always have a point. If I put a 0 in for x, I get a 1 for y. So they will always have the point 0, 1. So we can find out what the x shift is by looking how that changes. So let's take a look at this. We can see that the asymptote has shifted from y equal to 0 down to y equals, it's gone downward a -4. So that would put this as part of my equation. So now I know that g of x would be equal to 3. And I don't know what's happened to the x yet, but I know that the y has gone -4. There's my k value. Now let's figure out what happens to the x. Okay, so the point 0, 1 going down 4 should be at 0, -3. So here, because this point, 0, 1, would shift downward by 4, 1, 2, 3, 4. And the point is where I would expect it just alone from the y shift. So actually there is no x shift going on there. Otherwise the point would be shifted left or right, and it's not, so that's going to be my equation right there. Okay, let's look at the last problem. Once again, it's a logarithm. Notice that it's going to be a logarithm that has a fractional base, so we would expect that logarithm to come down and look like this. And the asymptote of this parent graph would be at x equal to 0. And so let's see where it is on the graph that's shown. And look, it's still at 0. So my asymptote here is at x equal to 0. So this thing does not have an x shift at all. So I'm going to go ahead and start putting my equation down here. So I know I've got log base 1/2 to the x, and the x is not going to have any shift. So I'm going to go ahead and just put it in parentheses like that, so I know I'm done with the x as far as that's concerned. And let's see where the y value has gone. So normally on all logarithms, remember they have the point 0, 1. And where is that point gone? Well, on the graph that they show, 0, 1 is, 1, 0. Right? Because if we put a 0 in for y, 1/2 to the 0 is equal to 1, right? So, and that point is still there. So that point hasn't shifted any. So I know that there is no plus or minus for the k value out here. But what has happened is you can see that I expected this thing to come down from the top and then swing out because of the fractional base. And it hasn't done that. It's actually flipped. So what's happened is this actually would have a negative in front of it because it's reflected across the x-axis, but the points themselves really didn't, that 1, 0 point really didn't flip. And so that's the equation of that. Next problem is a word problem. And it says, I purchased an antique lamp for $150. Okay, so let's go ahead and write, it sounds like I'm dealing with money. And does it talk about compounding? The value of the lamp decreases. I started with $150. The value of the lamp increases by 2.15% each year. And all we have to do is write an exponential model. It doesn't say that we actually have to solve it. So it's increasing yearly. There is no compounding. So my ending amount is going to be equal to my beginning amount times 1 plus the rate of increase in decimal form. So that'd be 0.0215 to the t years. So my ending amount would be equal to my beginning amount, $150, to 1.0215 to the t. And now if I knew how many years later they wanted us to value this, I could put a t in there and I would get the ending amount a, but that's all they ask for, so that problem is done. Okay, the next question, it talks about us getting a couple CDs, and we want to know the interest, and looks like what we need to find out is how much money is in each account at the end, and how much interest. That means how much does it grow. And so let's go ahead and for the top CD, what we have is we're going to have the amount, and it says it's compounded monthly. So what we're going to have is the starting amount that I deposit times 1 plus the interest rate, and the interest rate is 2%, and it's 36 months. Okay, and let's go ahead and just fill some of these numbers in. Well, no, let me go ahead and put the equation down. So 1 plus the interest rate all over n, so that's r, over n to the nt. That's my basic formula. Okay, so for the top one, and it does say that I deposit the minimum amount. So for the top one, I have a, the amount at the end, is equal to the principal, and it says the minimum amount is $1,500. Okay, so I'm going to put $1,500 in there. 1 plus the interest rate, which is 2%. So that's 0.02. It's compounded monthly, and it's got to stay in there for 36 months. Notice that it says 36 months. So that would be 12 times the number of compounding periods per year times the number of years, which would be 3. And so let's go ahead and work that out. I'm going to put on hold a second while I put. So when I plug those in my calculator, I got $1,592.68. Okay, now notice I want to bring up a point here. The interest rate that they're giving me is yearly. So the fact that it says 36 months, I need to change that into years. The fact that it's compounded every month is taken care of by these 12s. I still need to have this t value in years. So notice how I wrote the equation. Okay, let's go ahead and do the bottom one. Okay, so I'm going to have the ending amount is equal to the beginning amount, and if we look over here, I have a minimum of $2,000 that I have to put in the account. 1 plus, now my interest rate is 3% yearly, so that's 0.03. It's compounded monthly. And it says it's a 60-month CD. Okay, so it's for 60 months. So that would be 5 years. So that would be 12 times 5. And let's see what that equals. So when I plug those numbers in the calculator, I got $2,323.23. The last thing says describe the benefits and drawback. That's really not so important. Here are some things to consider. The second CD certainly makes more money. I have to put more money in, and because the interest rate is higher, so it's actually giving me a better return. I have $2,000 that I have to put in the account, so I have to put more money in it, which maybe is a drawback. I also have to keep the money locked up for 5 years, which would be indicative of the higher interest rate that it's going to pay me. The previous CD, or the first CD, it's not going to pay me as much interest. I don't have to put as much in, and I don't have need to have the money locked up as much. So if I don't need the money and I can put it away for 5 years, I would certainly want to put it in the second because I'm actually get a better return on my money. So let's see how much money I'm actually making on the two. That also says the interest. So on this one, it would be $1,592 minus the original investment. So the amount that I'm making on this first one would be $92.68. The amount that I'm making on the other one would be $323.23. So if you want to get a really good indication, you divide those by the number of years to see how much you're actually making per year. So let's go ahead and do that. So on the first one, you're making about $30.90 per year. On the other one, you're making $64.65 per year, looks like. And that looks like those are all the problems.